of this week, and it covers some topic to explain better what happens in the case of repeated eigenvalues for linear systems of ODEs. In particular, we're going to talk about Jordan forms, that is an extended way of talking about diagonalizable matrices. So when A is a square real matrix with size n and n linearly dependent eigenvectors, that means there are the same number of eigenvectors as the size of A, then we can write the diagonalization transform. So A equal T times D times T at the -1, where D is a diagonal matrix with only the eigenvalues of A on the diagonal. The fact that the eigenvalues might be repeated doesn't matter because anyway the eigenvectors are linearly independent. But in the case in which we don't have linearly independent eigenvectors, or some of the eigenvectors are not linearly independent, then we have a problem with this. We want to change the situation. If one of the eigenvectors, let's say xi1, so we reorder things in such a way that the first eigenvector is the one we're talking about. When xi1 has multiplicity higher than 1, so the associated eigenvalue has multiplicity higher and the associated eigenvalue has only one eigenvector, then T would have multiple columns that are exactly the same. That means that T is not invertible anymore. That means that A is not diagonalizable. Can we still do something about it? We can. It's called nearly diagonal matrices, and the idea is to not use a diagonal matrix D, but something similar, close enough to be diagonal. If lambda is of multiplicity m bigger than 1, with xi being the only associated eigenvector, that means there are less associated eigenvectors than the multiplicity of lambda, then what we can do is that we can define m-1 generalized eigenvectors. Generalized eigenvector solve this new equation. So you remember that for finding eigenvectors, the equation is A minus lambda I times xi equal to 0. Now we add a power to A minus lambda I. So in order to find eta k, for k going from 2 onwards, eta 1 is equal to xi, then we have to solve the linear system A minus lambda I at power k, eta k equal to 0. So we still have to solve a square linear system. As for the cases of eigenvectors, this linear system will be underdetermined, so there is a solution, but the solution is non-zero and it's scalable. If a vector is a solution, so is any multiple of that vector also a solution. And we should be able to circumvent the fact that xi appears multiple times as an eigenvector. Then we can write T is instead of xi1, xi2, and so forth, we add etas inside. Actually, here there is a typo. Eta 1 is equal to xi1, so the first column would be xi1 equal eta 1. Then the second column would be eta 2, and then we go up to eta k, all the k's up to eta m. So we have the first m columns bringing all the etas, and then we go back to the xi's. So the xi's are the normal eigenvectors, and the etas are the generalized eigenvectors. Then in this case, T, the matrix with the generalized eigenvectors in the right positions, is invertible. That means we can again write T and T inverse, and what holds is not AT equals T times D. We don't have a diagonal matrix anymore. We have what is called the Jordan matrix instead. So instead of having all the lambdas in the diagonal, we have a box of size m corresponding to the multiplicity of lambda that is not diagonal. And then the other eigenvalues properly on the diagonal as before. So what goes in this non-diagonal box? In this non-diagonal box, we call it the Jordan block associated with eigenvalue lambda, and we have lambda 1. We have lambda 1 on the diagonal of this m by m block, and 1 over the diagonal and 0 underneath. So this is a non-diagonal block, and it cannot be diagonalizable. We cannot change things in such a way that there are only elements in the diagonal. We have to keep those ones outside of the diagonal. For example, if we have A, the matrix of before, 1, minus 1, 1, 3, we have found that the eigenvector associated with the unique eigenvalue 2 is 1 minus 1. The generalized eigenvector that we can find is 0 minus 1. So T in this case has in the first column the eigenvector 1 minus 1, and in the second column the generalized eigenvector 0 minus 1. And when we want to multiply it in order to find A, we have the structure A times T equals T times the Jordan block. Is a 2 by 2 Jordan block associated with the eigenvalue 2. So this Jordan block, in this case it is equal to the Jordan matrix, it's 2, 1, 0, 2. So you see, it's not diagonal anymore. How does it get applied to ODEs? Well, we have the situation in which we have x prime equals ax. We want to apply the transformation x equals ty. Then we have ty prime equals a ty. We switch one t on the other side because in this new situation with generalized eigenvectors, t is invertible again, and we retrieve y primes equal jy instead of the diagonal. So in this case, we would get to y prime equals 2, 1, 0, 2 y. And if we start solving from the bottom, we have that y2 is equal to some constant, c2, exponential of 2t, and then we can use that solution to solve the previous equation. We have y prime equals 2y1, y1 prime, equals 2y1 plus y2 that we just computed. So we integrate this and we have y1 equals c1 exponential of 2t plus c2 t exponential of 2t. And this is the explanation of why we retrieve this t exponential of 2t from the previous versions. So now if we want to write the two fundamental solutions, so the fundamental solution set of this linear ODE, system of linear ODEs, then we have that y1 has is associated to the eigenvector 1, 0 times the exponential of 2, the eigenvalue, as times t, and y2 is t1 exponential of 2t. Then if we want to go back to solve for x instead of for y, we have to go through the transformation t again. So we have to remember that y is a solution of y prime equals jy, and we have x equals ty. So we have to multiply our solutions by t in order to solve for x. In a 3D example, just to make things clear about when we have multiple eigenvalues and eigenvectors, if we have x prime equals ax, where A is a 3 by 3 matrix that has only one eigenvalue, lambda, with associated eigenvector psi, well, we are in a situation in which we're missing two eigenvectors. We have one eigenvector out of the 3 that we need. So the situation would need that there are two generalized eigenvectors, eta 1, eta 2, or whatever you want to name them, and they solve A times lambda I eta 1 equal to psi, and A minus lambda I squared eta 2 equal to psi. Or, as we said before, we can also look at A minus lambda 1 squared eta 1 equal to 0, and A minus lambda I to the third eta 2 equal to 0. Then we can write T as psi eta 1, eta 2, and A becomes T times the Jordan block, the Jordan matrix, times T at the minus 1, where the Jordan matrix has only one Jordan block, and it's lambda 1, 1, 0 lambda 1, 0 0 lambda.